Another draft physics video production. For you, mostly. Anyway, just for you. Yeah, not really. Because it needs to be done. It's the kind of thing no one else is doing it, so I have to. It's just the truth. I have better things to do. Well, let's say, no, I don't have something necessarily better to do except to kill yourself, right? I mean, that's the only rational response to living in a cesspool. Yeah, it just seems like somebody's got to point this stuff out. And nobody's doing it, right? So I have to, right? Is there some alternative way of looking at it? I don't think so. So anyway, comments. So a comment I'll get back to that I missed, sort of. So this is an effect. So one of these things that happens, like the double slit or some other effect, some other, wow, isn't that strange? And it has a physical explanation, blah, 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 blah. And yet, you know, it's a little mysterious, so it's a little hard to conjure up a good one. And I'm just going to conjure up one. I'm saying, yes, it's physics. If you think about the object as being made of physical objects inside of it, and they all have different momentums and blah, 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 you can say, oh, yeah, well, it seems like, yeah, that could happen. It's not all that mysterious. But anyway, let's play with it. And such. I don't like that this is a very Tossium video, because he, of course, turns everything into some complex pile of mush. So not very useful, but it has the demonstration of the effect in it, so let's use that. Mostly. So far, so good. So the idea is it flips, you know, the wing nut flips its position, not that there's two wing nuts.
I want to thank the sponsor of this episode, LastPass, which remembers your passwords so you don't have to. More about them at the end of the show.
Yeah, fuck them too. Alright, so no, it'd be really cool is if they showed this in super slow motion. You know, that'd be another way to see some of the effects. So the idea is some astronaut for the Russians, whatever, 15 years ago or some wacky thing, saved the whatever Soyuz 7 space station-y thing or whatever, and it was undoing a package that was all wing nutted together, and the wing nut came off and flipped, and then flipped back again, and flipped again, and flipped.
What you were looking at is known as the Janabekov effect, or the tennis racket theorem, or the intermediate axis theorem. But we'll get to that.
Yeah, so why...
Now, you may have seen clips like this one before, but in this video...
so why not just show it in slow motion?
I will provide the best intuitive explanation of how this effect works. Or
it's not intuitive at all. Sorry, it's not really intuitive. So... if you get the idea.
Now, it involves arguably the best mathematician alive, Soviet-era secrets, and the end of the world.
Right, so they're telling us that we need a mathematician to have an intuitive explanation. But, so anyway, that's about it, right? You could see the thing wobbles and then flips, and then wobbles and then flips. So clearly it's a harmonic thing, okay? And if you think about the object, like think of it like a galaxy, and think about a galaxy being way out of balance. That is, it has more mass at one end than it has at the other end. And one end spinning, and the other end is wobbling a little. So further in the demonstration, I mean, he shows other things flipping, so maybe I can just find that. You know, you flip a tennis racket, maybe he has that in slow motion.
The paper says if you hold a tennis racket facing you and then flip it in the air like this, it not only rotates the way you intend it to, it also makes a half turn around an axis that passes through its handle. So the side that was originally...
Right, and I would argue that it doesn't do that if you perfectly throw it. So if you flip something perfectly, that is, the horizontal is perfectly horizontal to gravity and there's no imbalance, no difference in momentum. One side isn't going faster than the other. then it won't flip. It'll do exactly what it's supposed to do, which is make, just spin, and that's it. So clearly it's the imbalance to start with. And with the wing nut, the imbalance would be created by the last thread, right? The last thread, when the wing nut comes off, creates a little bit of extra momentum in one direction than in the other direction. So although it's spinning, it's got a bend in it, and it's processing in that bend. Now, the tricky part is why does it process so eccentrically? Well, you could say the eccentricity is almost like the eccentricity of the decay of an electron. Electrons don't decay in some perfect little spiral. They bend a lot, and then get into a little center. So this isn't something we haven't seen before. It's not like it's that mysterious. You could almost say that tornadoes do a little bit of this, in the sense that the cone gets wide with some eccentricity. So I would argue that it's just a harmonic thing, in the sense that you look for the fact that if you thought about it as little bits, that the little bits are going in different motions, different directions inside. And that because of the little bit imbalance you've created, you got a faster vibration, if you want to argue that's what it is, faster moving in one direction than you have in the other direction. So one side's moving faster, right? It's getting from point A to point B quicker than the other side is doing that. And that's creating this imbalance. And the imbalance isn't, the scale of imbalance is one of those curves, the ones that go to infinity. And so as soon as it gets to a certain stage in the imbalance, kind of like gravity, it starts getting very, very strong. So it's one of those R cubed kind of things, or R fourfold, or some other kind of thing, where the effect is magnified with every little bit of distortion. There's even more distortion. And I would argue that it's sort of a harmonic thing. So it's sort of stuff you can understand, that you can have a jiggling box and you can throw balls into it and one side will win. So there's a gravity argument that fits, sort of, in the sense that one side has to win. So like in orbits, if you throw stuff into gravity, you throw stuff going both ways into a gravitational field, the stuff will all end up going one way eventually, because the stuff will all collide and they'll make decisions, and essentially the math will be done, and one side always has a little bit more energy in it, and that little bit extra energy will decide that all of them all that survive end up going one way. And so it's sort of the same effect, in the sense that the motion in one direction ends up becoming a harmonic of the other. So they're out of phase, and then they become in phase, and that flips the object. So the vibration rate is such a way where it vibrates, anti-vibrates. The two vibrations are against each other, and then because of a timing issue, eventually they're both going up at the same time. That flips it over. So that would be my intuitive explanation. I think that's how an intuitive explanation should look. Okay, it shouldn't have mathematicians and all that crap in it. But anyway, so I think it's just that simple. It's a vibration. It does wobble first, and then it falls down. So again, you could argue it's a tipping point argument. There's a point where you tip it and it falls over. So it's doing just fine going like this, and all of a sudden it goes like that. So you can sort of understand it's sort of a dramatic difference between just doing this and all of a sudden doing that. One more little tiny piece of energy, and all of a sudden I fall straight down. And straight down, you could understand that if gravity's not causing that effect, some other force is causing it, that there's nothing to stop you from flipping right back over again and starting the whole process over, because again, you're going to have enough velocity to go too far, and then you're going to have to wobble back, and then you're going to be wobbling again, and you're going to flip again, and then you're going to flip, and then you're going to wobble and tip. So it's a tipping point harmonic kind of effect, I would argue. that if you really look at the roots of it, that's all it is. That there is a breaking point. You could argue glass. You can vibrate a piece of glass, right? You know, with a frequency. And you add one more little bit of frequency, and all of a sudden things start flying apart. They break into pieces. And once the fracturing starts, it just takes over. Same kind of argument, I suppose. Similar, not the same. So, yeah. So without going into a ton of details, I'm just saying that all these, everything, if you just think about it as the little bits inside are kind of like, they're connected, but they're like suns in the universe. They're like things bound with forces. They don't have to do exactly what they're told, in the sense that you can break the galaxy. If I wobble the galaxy, then there's a point where I'm going to wobble it, where the suns on one side of the galaxy aren't going to be in balance with the other suns on the other side of the galaxy, and their gravity is going to start causing accelerations. They're going to start magnifying the effects, and you could break the galaxy. You wobble the galaxy a little bit, and you could turn into a sphere or something, you know, for a temporary period of time, and then it would be flat this way, and then it would sphere, and you know, then go flat this way again. And you know, you can imagine different consequences of disturbing a system. So we're just really talking about what happens when you disturb the system. There's a disturbance. What does this disturbance add up to? What does it eventually do? Does it stay consistent, or does it get out of control? Almost like a piece of uranium, right? It's perfectly fine if you put it all by itself, but if you put it next to another piece of uranium, well, then they start accelerating each other's uraniumness, and they start decaying faster, so they change the rules. All right. I think that's enough without, you know, getting into a bunch of more complex ways of looking at things. I'm just saying, if you look at it as being bits that are more loosely held together than it appears. Obviously, when something's moving, the little bits have to do the moving. The little atoms and the little electrons are all getting pushed in directions, and there's forces that have to make them move, and the stuff in the center is doing something completely different than the stuff on the outside, in the sense that it's moving so much less. You know, it's just totally undisturbed by the event, where the stuff on the outside has obviously got a much higher velocity, and all those things are tied together by the tension between these objects, in the sense that they have this charge tension, and like little magnets. So again, you just have to think about the matter being a lot less rigid than it appears in its reality, because it's really made out of little independent bits that are being held together by stretchy kind of forces, and that you can start causing events where those forces get imbalanced to where the position of the objects are. So the forces are in the wrong places, and the objects end up behaving to the new location of the forces. Yeah, something like that. Alright, we already did that. No, we didn't do this one. Okay. Let's see. I'm in agreement with your quantum mechanics. I'm in agreement with you that quantum mechanics is complete nonsense. Now, that's not really what I'm saying. I mean, I've clearly said that if they kept it a quantum electrodynamics, that is, they recognize that, wow, there's all this wacky stuff that happens when photons interact with electrons. So depending on the state of an electron, all kinds of stuff can happen. You get all kinds of pattern. There's pattern created, okay, and there's an effect. So no, I'm not denying that, you know, there's all kinds of patterns being created by, there's pattern changes in photons as they interact with electrons. I'm clearly saying, yes, light does refract inside of stuff, and there is internal reflections, and there's all those kind of things that are happening. Those are real phenomenon, and I'm not denying any of that. I'm not saying any of that is wacky. I'm not saying the two-slit pattern doesn't happen, and it's not, wow, that's really bizarre. Bizarre in the sense that, whoa, you certainly wouldn't just sit there and look at it and say that's what should happen. So clearly something's happening, and it's the something I'm arguing is quantum electrodynamics, which is Feynman diagrams of the fact that photons interact with electrons, the electrons change, the photons change. Because electrons move much slower than photons, the energy is mixed with the electron's momentum, and you end up with a new momentum coming out. And that makes perfect sense to me. It fits. The Feynman diagram is essentially my boat diagram. Okay, you could just see the little squiggling thing is the swimmer. He jumps in the straight line boat and then squiggles out again in some new direction because the boat changed its position, but did it very slowly. All right, anyway. So I'm not saying it's complete, all of quantum mechanics is complete nonsense. Clearly we're talking about the part of quantum mechanics where they start explaining not just what happens, but why it happens, and their explanations of why are frankly incredible. I mean, they're extraordinarily complicated and screwed up and phantasmagorical, and those kinds of explanations should require extraordinary evidence. So if you're going to make extraordinary claims, which they are, there's new universes, radar, all kinds of, I mean, photons have mathematical skills, all this kind of bullshit. Well, you should have extraordinary evidence, and their evidence is less than ordinary, would be the argument. Plainly. It's not good evidence. It's not a videotape. It's not even close to a videotape. They barely have a smudgy fingerprint. I studied Newtonian physics in college and did really well, all A's. Well, what goes up comes down. Yeah, I mean, it's not hard to ace that one, But anyway, and then I got to relativity and quantum mechanics. It's really hard for me to say how I would have reacted. I mean, I was going to be taking all these courses when I was 20 years old. Well, actually, when I was 17, because I was going to college. Then, I was 17 when I graduated, and everything went wrong. Blah blah blah. Life crises. Blah blah blah. But yeah, it's hard for me to, I'm trying to, I try to, in hindsight, imagine how I would have reacted as a 17-year-old who I actually flunked a semester of physics in high school. But it was more just because I was a pothead, and the teacher hated my guts. He was a little bow tie wearing nerd, and we didn't get along at all. But anyway, I argued it up to a D. So, so they're clearly the fact is that I didn't buy these theories, and it's really hard to sit there and play their game. It's really hard for me to sit there and take a test on electromagnetic waves when I'm saying no, they're little bumps. That's what I was doing, and so it's hard to fill in the right answer when that's not the right answer. Just because they say so. So I don't know how I would have fared at college. Certainly I knew your obligation is to, do what they tell you, but I'm not really good at doing that. Frankly, I know that I have to do it, but it's like in the Army, I really wouldn't last to. I'd be peeling potatoes in the brig because there's a lot of that salute crap. Seems pretty gay to me. I ain't doing that shit. Fuck that. Anyway, it just isn't going to come out of me easy. I'm going to struggle with this. I got to salute you even though I don't know who the fuck you are, and somebody else put that fucking badge. What, Donald Trump put that badge on you? Fuck you. Cunt. I ain't saluting that shit. Anyway, I studied Newtonian physics in college and did really well, okay, always. And then I was able to bear the first half of the class, but dropped it at quantum mechanics because it was beyond obvious that the teacher was using his authority to feed us complete nonsense. I'm not doubting your reasoning. I think I would have found the math so convoluted that there's a point where you just say, I don't want to do this for the rest of my life. I mean, I really don't want to be playing with the world as if, oh, it's all these abstract bullshit. And I'm certainly not going to say a fucking electron has a frequency. You know, that kind of, so yeah, I would have a lot of trouble with it just because conceptually I just can't, it's like it was actually, if they actually made it angel talk and you had to actually talk in angel talk. Well, the head angel told Mrs. Frankenfire Angel that she had to do this, this, and this. And, it was that gay. And you'd just be like, I can't do this. It is incredibly gay mathematics. It's just frivolous and phony and fake and stupid crap jackass letters. It's just horrible. Anyway, he had a formula that was supposed to give us the mass of an electron. It had a variable n in it. He said n can be 1, 2, 3, 4, but he just let it be 2. Well, like I said, I have a whole problem with the games they play with the variables and the squaring of constants and all of that stuff. And you're saying, well, what's the gimmick there? What possible use could there be to squaring a constant? I mean, what's the gimmick? And it's got to be just a gimmick. So why don't you just forget that, because that's got to be circular and it's got to be a waste of time. So it seems you could get that step out of there where you square the constant. That seems like, wow, that step should be missable. Well, anyway, and he got the right answer for the mass of an electron. And again, how this whole idea that they can somehow measure the mass of a particle that frankly only has charge. I mean, it has no mass per se that's measurable beyond the fact that it has charge. Charge is the only interaction that's really taking place. So, I mean, gravity is a composite, okay? Gravity is an emergent force. It emerges out of the fact that electrons have the one reaction and protons have the opposite reaction. And when you mix them in semi-equal proportions, gravity will see it as a mixture, a dipole, and it will see it as neutral, charge-wise. But the fact is that there's no way to measure the mass of the electron because there's no gravity to really drop an electron in, technically. I mean, it's still there. I'm just saying that the argument is a little bit dicey because it's very difficult to create a pure field for an electron. You place an electron in the universe, it's not going to just sit there because there's always a bias. Venus is closer. Something's closer to it. There's a little more mass that way than that way, or that way than that way. And even, as I've explained, electrons can't stay in one place to save their life, so to speak. They have no choice but to move in all three dimensions all the time. And the point is, it's just how much they move. So here you're telling me you're going to measure the mass of something that's constantly changing its position. I don't think so. All right. I mean, you can't do it as a practical matter. So you're measuring something else. You're not measuring its mass. All right. And you got the right answer for the mass of the electron. Right answer compared to what? What experiment demonstrates the mass of the electron? I asked him why he chooses 2, and he said basically it's a nice number and some shit. Well, I don't know. Okay, so that's your story. I don't know if it exactly happened that way, but fine. So I left the class and left physics until I stumbled on DraftScience. Well, I would think your curiosity would still be piqued. About the real world. So to say you left physics, I mean, I frankly was never in physics, but I was always in physics. I mean, it's always something I've contemplated, is the physics of the physical universe, the physics of my physical function, my presence here. All of that is physics, and I have to say I've certainly studied it. I just haven't studied it by their lesson plan. Okay, their lesson plan, I think, is crap. Just as I don't do the English language the way the English would like me to. I mean, I invent my own more practical words, and I try to avoid their sissy words like instantaneous, and random. because those shitty things can't happen. All right, anyway. Moving on. More. Oh, okay. I came across you in your debate with Logan Blake. Well, that was sort of not relevant to this, but anyway, the vegan. Well, fake vegan? Okay. Well, anyway, I've been a vegan for 3.2 years, and you just came to that debate with nothing but facts and reasoning, so soon enough I became an ethicist. Good enough. Anyway, thanks for making these videos. I'm still not 100% sure about everything you're explaining. I'm not 100%, okay? I mean, the other day I started talking about, diffraction and reflection, and I started talking about how protons might be involved, and it's probably a dicey explanation, just because obviously photons don't hit protons 100% of the time, kind of thing, you could argue. So therefore, protons can't really be the explanation for reflections. But it fits a little bit, So some stuff I'm quite sure of, and some stuff I'm not so much sure of. And I think I point that out when I'm saying this stuff, which stuff I'm pretty confident about. But I'm going to keep trying to understand, yes. Ideally, I'll gain some authority if I graduate this year. Oh, okay, so you're still in school. Because I go to the #1 public university in America. Okay. And I am studying one of the most prestigious subjects, computer science and engineering. It's sort of not much anymore. But anyway, so yeah, it should be useful in life, I would imagine. So it will be hard for idiots to dismiss me. Well, if they can still outmath you, you're still in trouble. Of course, only idiots think having degrees means you're smarter. Well, frankly, I do think degrees mean something. I mean, it sure as hell helps to have 4 years of concentrated focus and all that kind of stuff. And the real problem are the idiots who think they went to college when they didn't, They're the dangerous ones. Now, I happen to be, very good at it. They just happen to suck at it. The armchair, doers of the world. I happen to do stuff that I actually know how to do. Yeah, I actually do know how to do it. Yeah. I must admit, these videos are hard to follow. Well, I don't know why, but, 2 + 2 + 2 physics? Shit, sort of made it really easy. Jumping in a boat, jumping out of a boat, that's fucking pretty easy. But anyway, so I might start making simpler, easier to understand videos on the subject eventually. Well, making videos is a good idea. Talking is a good idea. Arguing is a good idea. Yeah, that's the only way anything gets done, is you got to do that stuff. And that's the stuff that's missing from the world. There really isn't enough of that going on here. In spite of having all of these ways to do it. And it just isn't happening. Which is really disappointing. Okay, you realize GR's prediction of gravitational lensing was verified in 1919, right? Well, you realize that the guy who did the experiment was a huge fan of Einstein's, one of the first and only, and admitted in his own journal that he wouldn't stake his life on the results, and that there's lots of talk out there in the world about how there was some shenanigans because the two different sites for gaining evidence or information were in conflict, some of their slides, and there was dispute over which ones were kept and which ones were thrown in the garbage, and it seems clear that the ones that were thrown in the garbage are the ones that didn't verify the theory. So it was kind of messy. It's clear what the weather was. The weather was the weather. The fact is he got slides that were maybe 20% as good as he had hoped. Maybe. It might have been as bad as 10. Really bad. Okay? Not very optimum experimental results. And that the experiment hasn't been successfully, in the sense of past the margin of error, been duplicated since. And even though we have all these satellites in space, thousands of them, with really good cameras, weather, national weather satellites, good cameras. Nobody's turned one of those cameras around just to do a quick little look, take a few little photographs, and see if they could verify this lensing event. None. None. Zero. So you realize all that, right? That the scientific method is duplicating an experiment. That's one of the fundamental things, to be able to redo it again and to get the same results and all that kind of crap. You do realize that, right? Butt shit. Matthew? Do you realize that? Question mark. Okay, you're in denial of the nature of this universe, which I imagine you think is what? What, do you believe in multiverses, little sissy boy? Huh? Yeah. What, you believe in the head angel? I mean, what you believe photons don't know where they are? They're in a mystery cloud. And then when they go through the single slit, they, for some mysterious reason, decide to split into two thingings that aren't them. They're magical thingies, wavical thingies, and those little wavical thingies somehow interact as if they were a big giant wave of something. And then land in one discrete tiny location. And all the other stuff they did, going to Venus, they just said, no, stop doing that. Pretend you never went there. You never used any gasoline to head that way, because we've decided to go this way. I mean, the whole thing is shit. It's shit. Alright, seek mental help. I think you need it. You're eating shit. You're talking shit. You're full of shit. Yeah. Fuck you. There. I'll see if he comes back to try again. Try again. Yeah, that was fairly lame. Anyway. Thank you. Really appreciate the much more logical explanations for some of the quantum woo-woo out there. Well, thanks. It's okay. Somebody's got to do it. This web page is slowing down your browser. Yeah, well, because it's fucking made by Google. It's spying on everything I do. Oh, when he clicked the delete button, he spirals around a little bit, so we should put our ads over here, because people spiral to the left when they click a link more than they spiral to the right when they click a link. They're actually doing that. They're actually watching everywhere the mouse goes, so they can figure out how to make you accidentally click shit like, sell your house to us. Alright, so I did that. It never seemed to be done. I don't know, it shouldn't really be done. I guess I could go back to the beginning, but maybe we'll clean up this other crap to clean up. I think this is here somewhere. He made some other Google talk. I have to go find it and make fun of that. I mean, scrutinize the authority. Alright, so let's do this quantum mechanics 1.3, the third part of this troll's argument. Videos about science stuff. I mean, I love that. Yeah, it's stuff. Science please, he calls himself. And, just an arrogant turd. So, we'll click on that.
Hopefully you'll remember from Quantum Mechanics 1.2 that we just got done looking at Max Planck's solution to the ultraviolet catastrophe. After Max Planck had solved the ultraviolet catastrophe...
It's like you got that thunderfoot disease or whatever. So, well, that's just... There was no catastrophe, except the catastrophe of having silly expectations that it's just as easy to make this vibration as it is to make a billion gigahertz vibration. That the two are mechanically the same or something, that there's just a vibration and it frankly doesn't make any difference. Well, that would be a stupid expectation. The higher frequency is harder to manufacture because it requires velocities. Okay, much higher velocities.
his work on the subject went unspoken about for quite a while. Planck's trick of putting the energy of light into little packets was regarded by himself and most of his colleagues as just that, a trick.
Yes, and the trick is, look, there's a real functional trick to the fact that we can only see it in packages. So that's part of the gimmick here. Now, I'm arguing that it is in these clumps. I'm just pointing out that, to be fair, the evidence that it's in a clump kind of sucks, because the evidence that it's in a clump is the fact that we can only see it when it's a clump. You get it? It's not very good evidence. It has to do with how electrons are affected, and they require a clump of energy to be affected. And that's just the truth, okay? But there could be smaller clumps that aren't affecting the electron, and we would have no way of detecting them. We can only detect the tip. So anything that wobbles the electron, we have no clue. Just wobbles in certain ways. We can only see certain kinds of disturbances in an electron. Other disturbances we can't see.
But as far back as 1887, evidence was being collected for a phenomenon that would take Planck's trick to new heights and lead to the birth of wave-particle duality. The photoelectric...
Which is the birth of what? A complete mutant bastard, deformed pile of crap. Wave-particle duality. This is nonsensical mush.
Effect was what sparked Einstein to postulate that Planck's light quanta were physical particles. Physicists at the time were really excited about playing around with electricity and doing all sorts of experiments with it. It turned out that if you had a piece of metal and irradiated it with light, you could measure a current flow from it.
Right, now this is the funny part, right? Is they say, well, you need quantum mechanics to make this and to do transistors and all this. This is the origin of the transistor right here, okay? You put a little energy in one place, you get more energy out another place. So in a sense, this was, and it's the photodiode. This is essentially a photodiode right here. There's the blueprint of it. So they already had solid-state electronics, before they'd even gotten quantum mechanics. They just hadn't been able to turn it into a more practical form. But they already had the mechanics. They already had a demonstration of it right in front of their faces.
Electrons were somehow being ejected from the metal surface when exposed to light. We now call these photoelectrons. Now, this effect wasn't impossible at all with the current understanding that...
So we call them photoelectrons. They're either are electrons or they're not electrons, right? There's no such thing as a photoelectron. So let's understand what it causes is a current. Or it causes an ejection. So now he's showing two different effects, right? One effect is you shine light on and you eject an electron. And the other effect is you move current through a wire, an electrical effect. So one has to do with atoms conducting. That means one atom pressurizes, it shares its pressure with the next atom shares the pressure with the next atom, and it moves down the low pressure line. And the other effect is clearly ionizing a substance, in sense of, for a while anyway, the electron is moved away from the atom, it's ionized, and then it moves back again. They're different effects, but they don't make any distinction.
Of electromagnetic theory and the structure of metals. Physicists at the time had a half-decent model for metallic structure called the Drude model. This was heavily inspired by the statistical mechanics being developed.
So he says it's an okay model, blah, 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 but, who's judging whether it's an okay model? So this idea that electrons are blobbing around, I think it's a bad idea. It seems clear that electrons do move to where the force pushes them. They don't get to decide anything. The force tells them what they're going to do and where they're going to go. The swimmers in the ocean will decide which way the boat ends up rowing. That's the way it works. The boat just lets the swimmer jump in if he bangs into it. So if the swimmer bangs into the boat, he jumps in, he kicks the opposite going guy out. That's how the boat works. And the only thing that decides where the boat goes is obviously what's in the water.
time. So whilst it was possible under the current theory that electrons could be emitted, many of the observations that followed were simply not possible under the Maxwellian theory of light. The physicists investigating this phenomenon found that, firstly, emission of electrons only occurred when the frequency of the incident light was above a certain threshold frequency.
Right, so again, this is just kind of obvious. You have something in tension, and that's essentially what, something that's standing up in gravity is in a kind of tension. You move it a little bit this way, it falls down. You move it a little bit that way, it falls down. And all you're doing to an electron is wobbling its tension. You're stressing its tension. You're pushing on its rubber band and seeing if you can break it. I mean, I hate to use the rubber band analogy, but anyway. And so you find that you can do that with certain frequencies. Certain frequencies are more likely to tip something over than other frequencies. If I've done this so many times, but it's this simple, right? I mean, you can get the idea. If I'm hitting something rather slowly, then it tips when it gets hit, and it goes back. And then you hit it again, and it tips, and it goes back. And that's all you get out of it. But if you increase the frequency just a little bit, right, then you hit it before it only gets halfway back. And then you hit it again. And then it only gets halfway back. And then you hit it, and then you tip it. So higher frequencies are more likely to tip objects. And they're more likely to eject electrons. So there's nothing dramatically unintuitive about this fact.
Depended on the material. For most metals, it's usually somewhere in the ultraviolet region or above.
Right, so this would be, they're just pointing out that each metal is a different configuration of atoms and compound in the sense that they're stuck to each other through atomic function, and then their composite is different. The electrons and the protons are also in a different relationship, a different amount of tension. So for each metal there'd be a different amount of tension. So therefore it's just saying the weight of the pedestal you're going to knock over is heavier, and you have to have a different frequency to knock it over.
Secondly, the maximum kinetic energy of the emitted electrons wasn't affected by the intensity of the incident light.
So what they're saying by intensity is the number. So the amount of tennis balls you're throwing at something doesn't make a difference if it's the wrong frequency. That's all it's saying. And so if you're just doing this, you just keep hitting it too slowly, right? You're not going to get anywhere. But if you hit it constructively, that is, you put momentum in when it's already going the right way, and you add completely more energy to the system, well, then you can cause more wobble. It's that simple.
The current amplitude would increase, but the maximum kinetic energy of the electrons remained constant for a given frequency. And lastly, the time between light being exposed to the surface and emission of electrons was practically instantaneous. It is, of course...
So that's just more nonsense talk, right? I mean, photons move practically instantaneously, okay, from our perspective, but they obviously don't move instantaneously. There's no point ever using this stupid word, practically instantaneously. There's no special speed. So that again is nonsense. But obviously if you're constructively adding to the tip, that means you're increasing velocity. That's like gravity adds to your velocity if you're falling in gravity. Now if I stop you from falling, there's no more addition. You're just moving 10 meters per second right now, and you're denting your chair with that. But you don't have any extra. You can't keep adding velocity because you keep being stopped. You keep being pushed the other way. But if something can keep pushing you in a direction, like gravity keeps pushing you because you're falling, well then your velocity keeps increasing, and the same thing happens to the electron. Its velocity increases if you're going to tip it.
Was finite, somewhere around 10 to the minus 16, which is incredibly small. None of these experimental observations...
Yeah, well, no one would expect it to take very long for an electron to get emitted from an atom. So yes, obviously it doesn't have to move very far to be out of the atom. I mean, we're back to this. Atom is to an apple what an apple is to the earth. I mean, it's, you don't have to move very far, and you're not in the atom anymore.
observations were accounted for by the classical Maxwellian theory of light. Einstein, however, was able to account for these observations. He postulated that Planck's light quanta were physical particles. Instead of thinking of light as a wave, it could be considered something akin to an electron or a proton.
It could be thought of as akin to something coming at a frequency. But again, this really doesn't have anything to do with it, because the point is that it just takes a certain amount of momentum in the electron for the electron to get free. So if you can maintain its momentum and it can gain velocity, just like the Earth, you can't get a rocket off the Earth without enough fuel. So you don't have enough fuel, you're going back. If you have enough fuel, you get free. Now, somebody looking on the outside could say, well, there's a certain amount of fuel chunk you need to get out of the Earth. That doesn't mean the fuel is made out of chunks. That doesn't, it doesn't mean that there's just one chunk of fuel, So I'm just saying that this isn't very good proof that the energy comes in clumps. And clearly, I don't think Einstein's understanding of the photon as a clump was it's a clump at a frequency. I don't think Einstein said that. So I don't think he was still thinking about what a frequency is in the right way, in that what makes this was always something I had a problem with, because even if I thought of the frequency being the size of the quanta, it makes no sense to have a clump of something, a piece of jello, a piece of whatever, that would be 10 miles long. A radio wave can be 10 miles between the clumps. It's so distant. It takes, the speed of light would move 10 miles in the time there is between the clumps coming. And thinking about something having a frequency that's 10 miles long, come on, it seriously doesn't make much sense. Obviously, they're just cannonballs, and there's 10 miles between them in terms of how many miles are traveled before you fire the next cannonball.
But most importantly, for a given frequency nu, a photon would have a well-defined energy h nu.
So this was where they started turning frequency into the relevant factor, rather than recognizing that, of course, it's relevant. It is going to be able to manifest the tip or not. No tip is going to be completely dependent on that frequency thing. But that doesn't describe the things that are actually knocking it over. So again, it doesn't matter. The tennis ball just happens to have more energy, okay, when you're trying to tip something over. It's not intrinsically any different. Now, obviously, tennis balls that are a mile apart and tennis balls that are 1 foot apart, that in any moment of time, if you're throwing them 1 foot apart, you're going to throw a hell of a lot more tennis balls. So, of course, it's going to have more overt energy in a moment of time if it was a continuous ray. But the point is, this has nothing to do with that. The photon doesn't have intrinsically any more energy by giving it a higher frequency. It's just that it can have more effects. And that's where they're drawing the wrong conclusion. They're saying the energy is in the photon. The energy is just in the frequency. In the sense of it's just dependent on the fact that you can tip things over. If there's nothing to tip over, you won't notice the difference.
Einstein proposed a mechanism by which photoelectric emission could occur. When a photon is incident on a metal, it can penetrate into the surface where it has a probability of being absorbed by an electron in the delocalized C. The electron will gain an energy equal to h nu.
So this delocalized C doesn't really mean anything. That's just saying there's electrons that aren't bound very rigidly, and they are kickable.
And then undergo transport out of the metal lattice to cause photoelectric emission. The electron, however, will have to do some work to overcome the attraction to the positive ions to keep it bound in the overall structure. So the point is that you can go pretty high into the atmosphere and we can see it, and so we register the event, but the electron's still going back home. So you haven't given it escape velocity. You've only given it enough velocity to get to the high atmosphere and say, hi, I'm here, and then you're going back. The maximum kinetic energy of the photoelectrons will be the energy imparted on it by the photon, h nu, minus the energy required to leave the metal. something we call the work function phi. The electrons therefore won't be able to leave the metal unless they have enough energy to overcome the work function. The minimum frequency nu.
So the work function just means that they're going to apply another force against the electron and just measure how well it penetrates that force, and that'll tell its momentum. So they're just putting an airbag there and seeing how much air the electron will displace, that kind of thing. So they're just giving a proportional force against its movement, and just saying how much force against its movement do you have to apply, okay, to stop it from moving, and that will tell you what its momentum was, which is not wrong.
Naught requires the electrons to overcome the work function will be when their maximum kinetic energy is 0. So this frequency nu naught is given by phi over Planck's constant. So we see Einstein's model predicts the existence of a threshold frequency, a minimum frequency required to observe photoelectric emission.
Right, so this is just telling you, again, it's just the tipping point argument. There's a certain amount of fuel you have to escape gravity, and you can't have less fuel than that. If you have less fuel than that, you're going home. Probably unpleasantly.
Depends on the material being used, as phi is a property of the metal. Under this mechanism of photoelectric emission, the intensity of the incident radiation wouldn't have any effect on the maximum kinetic energy of the photoelectrons, but it would increase the amplitude of the current, since there would be more photons to be absorbed by electrons in the metal.
Right, so this is just an argument about how many electrons you're affecting versus trying to affect the individual electrons more aggressively. So the point is you either get into space or you don't. We're not really measuring anything else. Just trying to think through the argument, though. The argument is if you increase the frequency, you will increase the momentum of the electron and it will travel further. So what he's saying is only true when you don't change the frequency. As you change the frequency, you do change these effects. But the amount of effect, that is the amount of photons you send, so there's two ways to send the energy. You can send it at a higher frequency, or you can send more of it. So when you send more, if you're over the threshold, then you'll create more current. That is, you'll move more electrons, obviously. And if you send a higher frequency, you'll expel the electrons further away, but not more of them.
Now, any good theory should produce a plethora of experimentally verifiable results, even if the theory turns out to be wrong. If it produces well-defined predictions that can be tested.
So again, this testing predictions, it all depends on how much scrutiny you apply to that, right? So this is like back to the single impediment, creating exactly the same pattern as the single slit, indicating that it's about surfaces. But you have to put those two things together. Now, if you look at your evidence without putting those two experiments together, then you're going to draw wrong conclusions, right? The key variable in the equation is the distance between the surfaces, not the distance of an opening, just the distance of the surfaces. That's deciding the effect. So how you scrutinize the evidence is insanely important. And just predicting, okay, saying there will be an effect, well, I can do that. Okay? You don't need to be a nuclear physicist to do these predicting. They're just saying, I have a gambling house and there's going to be, you know that every single device is going to have a gimmick to it, a mechanism. And it's pretty easy to figure out what the mechanism is, and they're sitting there applauding their physics because they figured out it's a gambling house and there's gimmicks of odds. Whether you're rolling dice or spinning a ball around a wheel, that all of that just equals randomizing outcomes.
By scientific standards, it's a good theory. For a textbook example of a theory that's good but not correct, see the steady state theory in cosmology.
Well, I'm just arguing that this theory is good but incorrect also. The wrong deductions have been deduced in the sense that this is somehow evidence that the energy is quantized, when really what you've done is you have evidence that the effect is quantized. That escaping gravity is different than not escaping gravity. And just because you can't see not escaping gravity, you're saying There's only escape gravity or no escape gravity. There's nothing in between. But there is nothing in between. But the point is you can't see all the energy that happened, okay, that's invisible to you.
To test Einstein's theory, we could imagine having a glass vacuum chamber with a metal cathode at one end and an anode at the other end, connected to an ammeter and a variable voltage source. If we don't apply any potential difference across the electrodes, and then irradiate the cathode with some electromagnetic radiation, we can expect to see a current when the frequency of the radiation is above the threshold frequency. Once photoelectric current is flowing, we could increase the potential across the electrodes.
They're just saying instead of using electricity to create a voltage difference, you're basically using photons to create the voltage difference, which means you're going to create in the atmosphere that'll have to exist, some atmosphere, that there's going to be a transfer of the energy through that atmosphere, those atoms, a plasma of some kind. Something's going to have to be created, and they use the flow of electrons. So let's just say the flow of electrons. So instead of using voltage to stimulate it, you're stimulating it with photons and just basically measuring the voltage you receive as a byproduct of hitting it with the photons.
In a negative polarity, so the electrons have to do work to overcome the potential.
So now you're just saying I'm going to hit it with the light and then I'm going to apply an opposite voltage. And so now the electrons are not seeing a clear anode. Okay, so they're getting ejected, but there's no direction they're getting injected in the sense that the voltage isn't consistently pushing them. The force is pushing them the opposite way once they get ejected. So you're just replacing the proton's restorative field with, so it's something shoots out of gravity, and again you just show up with a rocket and try to push the rocket back into gravity. So you duplicate what gravity does, but you're duplicating it with an artificial rocket. So you're extending the Earth's gravity in a sense, and you can measure how much you had to extend it, would tell you how much momentum the rocket had.
The potential difference is the work done per unit charge. The work done by the electrons would be E times the potential difference. We could then keep increasing the voltage in the negative sense until no current is observed at some negative potential V naught. At this point, the electrons have expended all of their kinetic energy in doing work against the potential. This is what's called a stopping potential. Since at this point the maximum kinetic energy is equal to EV naught.
So you're just basically saying you have a voltage created by the electrons that might be 10 volts. You're trying to apply the opposite amount of voltage to stop the electrons from arriving. So you're basically neutralizing all of their momentum so they never get to where they were going. So there's no voltage. And all you have is your 10 volts that you're putting in.
And relate the stopping potential to the frequency of the incident radiation and the work function. Since E, H, and phi are constant, we have a linear relationship between V naught and nu. So if we then change the frequency a bit and readjust the voltage to obtain a new stopping potential, we can gain a series of measurements of V naught and nu. If the theory's predictions are correct, plotting these on a graph should...
Yes, and I don't know why they plot it on a graph negative, because there's just no point in having to do that, but whatever. It's obviously a linear kind of line that'll tell you as you increase frequency, you increase the momentum of the electrons that are being ejected. That is, as you increase the frequency, you increase the velocity of the motion tipping it. Just as your velocity increases as you free fall in gravity.
Should give a linear relationship. Of course, if you do this experiment, you'll find exactly that. The theory makes such precise predictions.
So there's just nothing, this theory predicts something quite obvious. I mean, it's kind of obvious. If it's coming at more frequency, then there's more impacts per time, and obviously you're going to be adding more velocity. So it's like me changing gravity and making it stronger, and saying I made a brilliant prediction because I made the gravity stronger and the thing moved faster. That correlation is just too obvious. I mean, it's too obvious to sit there and say, wow, our physics must be all right because we predicted something so frickin' obvious.
each of which are experimentally verified, it's hard not to be convinced that light has at least some kind of particle-like nature. The kind of behavior...
So again, as much as I sympathize with this argument, in the sense that that's what you should believe, it has a particle nature, but for other reasons, this is not a very good proof. And I'm surprised they even concede to this proof, in the sense that it's not a very good proof.
in which light is considered both a wave and a particle is what's called wave-particle duality.
Which is just silly. And again, they don't believe it, so why do they even say it, right? I mean, you know, people like Professor Lewin say, this was nail, you know, from the Young experiment, this was nail in the coffin evidence that light is a wave. I mean, he says it. They say it. Everything they do in their physics has all these waves all over the place. They call it the wave equation. I mean, they don't call it the force equation or something else, or the interaction equation. No, they give it this stupid name, even though there's no wave in the actual equation. There's a frequency, or there's a angle, you know, sine theta. There's no frickin' wave anywhere.
Unsurprisingly. The evidence for wave-particle duality doesn't stop at the photoelectric effect. Another significant phenomenon is Compton scattering, named after Arthur Compton. If light really does behave like a particle, then surely it should engage in some other particle-like phenomena. One of the simplest ways two particles can interact with each other is by colliding and bouncing off of each other.
Right, but see, this is the catch, that if you thought of that in pure kinetics, that is something that's purely kinetic, then like purely kinetic pool balls or something, the ones that have no spin and no, you don't have to wait for the energy to vibrate through the ball and create distorted effects. So if it's purely kinetic, whatever goes in, exactly the same thing comes out. It's just that they've exchanged places. So this one can be going 100 miles an hour, and this one can be going 10 this way. And what'll come out is this one will end up going 100 miles that way, and this one will end up going 10 miles an hour that way. They'll just exchange the role perfectly, like in a Newton's cradle.
Process physicists call scattering. Compton scattering is one such process. It needs both wave-particle duality and special relativity to explain it.
No, you don't need any of that crap. I mean, again, that's just nonsense. You don't need it.
You could consider a photon with some energy h nu colliding with a stationary electron.
So again, we're back to h nu, which again is just another way of saying it's frequency dependent, because that they're going to turn that into a frequency is the only thing they're measuring, really. The only thing they're giving energy to. They're not really establishing that this is the energy. The humps are the form of the energy. And all you're really doing is hitting something at these peaks.
In a special relativistic context, the total energy squared of a body of mass m and momentum p is given by the equation E squared equals p squared c squared plus...
So, and again, they just draw this, right, this little humpy line, and they never show the length of it. They never deal with the fact that this light, this wave, comes in a ray form. That is, there's an amount of it. That there are really no continuous sources. They're in rays of stuff, little bursts of it. And that's going to also decide how much energy there is how much ray is there.
m squared c to the 4. The incoming photon is massless, so it has energy E equals pc equals h nu. The electron...
So it's massless, and yet it, you know, again, they invent a mass for it because they can't give it any momentum without mass. So this doesn't make any sense. They can't say it's massless. It's stupid. It's impossible to have momentum and no mass. It's not possible.
On the other hand, is at rest and has no momentum, so it has energy equal to its mass times c squared. If the photon acts like a particle, then it should scatter.
Photons only have zero mass if you can imagine them not moving. So that's the bullshit of this. They're saying it has no mass. Well, yes, it has no rest mass, but it's never at rest. So again, this argument that somehow there's a rest point for a photon, there's some point in its existence where it rests somewhere, where it doesn't move, is ludicrous. So you always have to measure its mass based on its momentum. And that's always consistently the speed of light, so it's pretty obvious that it has a calculable mass.
off the electron, imparting some momentum on it, and recoiling at some angle theta. The photon has now lost energy to the electron, so in order to conserve energy...
So again, the photon doesn't exist now. Okay, the photon is absorbed by the electron. That's it. And if the electron isn't compelled to go back to an atom, if it isn't in some field that is against it, that is, there's more swimmers coming towards it than away from it, that's all that's going to decide what happens here. A photon's not going to be, this is happening inside of an atom. This isn't, the Compton scattering happens to atoms. Okay, it doesn't happen to electrons. It happens to atoms. Atoms scatter light. Electrons are the mechanism, but it has to be an electron bound in an atom. So again, this drawing is just completely eliminated the electron's attachment to the proton, which is going to be the thing that recreates the new photon. So the scatter doesn't happen anything like this. The electron absorbs the momentum, moves away from the proton, then when it moves back to the proton, that's when it's ejecting the energy it absorbed. It absorbed energy to go this way, okay, and now it's going to give back the energy when it goes this way. It's going to leave a bunch of swimmers going the opposite way.
Its frequency must change to some new frequency, nu prime. If we apply conservation of momentum and energy, we can show that the change in wavelength is h over mec squared times...
So again, they're using the wavelength to define the energy. And again, the energy is in the tennis balls. The frequency doesn't make the tennis balls give them more momentum. But as a collection, it can give them more effect on an electron.
1 minus cos theta. I'll leave the working out of this to a special relativity series, but it's not too hard to show. This change in wavelength is going to be of the order 10 to the minus 12 meters. In order for this to be comparable to the initial wavelength, Compton scattering is best done with X-rays or gamma rays, which have similar or smaller wavelength. Compton scattering is in effect... So
essentially what he's saying is when the photon goes in, it's absorbed by an electron. The electron moves to a new position, then re-emits the photon. Now it's emitted the photon in a new direction, but it's also changed the frequency of the new photon. So when it's going back, the going back speed is different than the going out speed, is essentially the point being made. And that going back speed really just has to do with how much is in the field of the electrons and the protons of the atoms. So depending on the material, you'll get a different frequency shift. So depending on what kind of particle it hits, you're going to change also what the frequency of the light is.
It's always of consideration when light interacts with matter. And you may be thinking, how can light both scatter off electrons in Compton scattering and be absorbed by them in the photoelectric effect? Well, this is all down to the probabilistic nature of quantum mechanics. There are lots...
So this is just more nonsense. It's obviously the electrons are... Even if you kick an electron actually out of an atom, then you've left a place where there's a field of a proton that can be filled by an electron. So you can't really undo, okay, a force. The force has to be understood as something. If more swimmers jump in a boat and the boat's going this way, I can be guaranteed that somewhere over here, okay, there's more swimmers in the ocean going this way, or they're in a boat and the electron's moving that way. You can't get rid of the yin-yang thing.
Lots of different ways in which a photon can interact with an electron. Some are just far more likely than others under certain conditions. But in principle, a number of different interactions will occur when, say, X-rays are fired at a metal surface. In fact, Compton scattering will occur if you do a photoelectric experiment, but it's usually of secondary, if any, importance and won't add too much error to your experiment. But it is happening. Clearly... So
he's just pointing out that the higher the energy, the more you can see this change, because the more dramatic the change is. But that's all.
There's a lot of evidence for light acting as a particle, so we'd be justified in asking, is the converse true? Are there particles that act like waves?
So again, they've drawn the particle as a wave, right? Which doesn't make any sense. They've totally ignored the length of the wave, like how much is in it. How do you particleize a photon? Again, does that mean that the photons for radio waves are, 10 miles long, a little tiny thin thing or something? Come on. No, it doesn't mean any of that. It just means the tennis balls are further apart. Period. Cannonballs, bullets. You fire to them at a different rate. That's all it is. But they're the quanta. What they do to an electron doesn't define them. It defines what an electron is. Okay, electron has peculiarities of its circumstances. The boat can have different directions, different things, and it can be in fields where there's a bunch of swimmers going this way or that way, and it can be in tensions, because of charge, because the proton is doing exactly the opposite of what the electron. So again, they're talking about what electrons do when they're bound to atoms, and they're just pretending they're talking about what electrons do. You can't do it that way. You can't talk about an electron and say this is what an electron is, when what you're really saying, this is what an electron is when it's attached to a proton. And those are fundamentally different, you will concede, right?
Yes, all of them. But like almost always, we really only care about electrons. If there were one phenomena we had to pick to test if particles could...
Well, again, Dan, we only care about electrons because electrons are on the outside of the atom, and they're the things you're more likely to interact with, and that's really all that's about. And I would also say that electrons, I would speculate, 70% assurance, that electrons have this odd thing where the number of seats in the boat is an odd number, and therefore electrons are always moving, and protons have an even number, so they can be 3 and 3. They can stay neutral. They don't have to jiggle all the time. Not that they don't jiggle a lot, but they don't jiggle as way less than an electron does.
Act like waves, it would surely be diffraction, which makes sense as diffraction is only caused by waves. Diffraction is when a wave, say...
So when he says these kind of words, right, diffraction is a concept, okay? It's an effect. Diffraction is an effect, and the effect is that the angle of trajectory is changed. That's what diffraction is. It's an effect. They've now said the word is owned by waves, and only waves diffract. I mean, that's just cheating horribly. To steal a word like that and pretend that the only way diffraction could ever be understood is by understanding it in a wave context. I think that's just unfair. Cheaters. Steal a word like that. Can I say that refraction is only in particles, and therefore you could never talk about a wave refracting? I mean, it's just cheating.
Like light passes through a slit or around an object, causing it to bend. The most important case is really when light passes through a slit.
Yeah, so obviously they've changed now the wave into some sort of forever straight liney thing, right? It's not a ray. It's not going through one place in space. It's not doing any of that. Somehow it's a billion photons. When we know that if we do this with single photons, the diagram is going to be is that, well, one of the first photon might go that way. I guess I can use the mouse. Right? The first photon might go this way. The next photon might come out straight. The next photon will come out this way. The next one comes out this way. The next one lands this way. That's what we'll see. Okay? If we send one photon at a time, what we will see is photons landing in all of these positions. And that's what they'll do. They'll land in all of these positions. There won't be any... Well, we know what's going to happen, though, right? We know that in water waves, this is what it looks like. In light waves, it doesn't do this. So, again, it doesn't just diffract. That is, it doesn't just spread. It spreads at particular angles. So we know that the angle is going to be 3 degrees. If I went degrees from this side over, and I called this 180 degrees, right? So we know it's always going to be multiples of 3. So it's going to be 3, 6, 9, 12, 15. It's always going to be in multiples of 3, right? It's always going to be some multiple of the same angle. And those are the paths the photons will take. So no matter where they go in here, they'll take one of those angular paths. All right? That's the diffraction.
If we send a beam of light through a very narrow slit and then observe it at some distance away on a screen, we see fringes of light and dark. When the light passes through the slit, it bends and spreads out. The smaller the slit, the more...
So again, they say it bends and spreads out. What they're saying is, no, it splits into two waves, and they create these two waves. Okay, just completely artificial. So one photon goes in, creates two waves through some miracle. The two waves have this interference bullshit, and that's what's creating these distinctions. And what I'm arguing is this is the simplest pattern you can get, on, off, and that it's completely angular. That is, except for this larger center thing, it's completely symmetrical. So it's always 3, 6, 9, 12, 15. It's always a multiple in the sine theta. And so it's not a complex pattern at all. And I'm obviously arguing that depending on where you go through will increase the likelihood that you hit, like, say, more than one electron. So for each electron you hit, it's a 3-degree shift in your position. And that explanation solves the problem. And the fact is they've never really done the experiment. See, by their theory, there should be photons going here. Just as likely, in a sense, as, not just as likely, but by their own probability, it's something that should happen. So just put a piece of film over here and see how many photons ever go this way, and that'll tell you something. Because I would argue that if it was hitting electrons, there's no chance you're going to get a photon over here. So that's a simple experiment they can do to verify, to glean more information, to find out more about what's going on. But they don't do any of these experiments. None of them. Because they have a conclusion, they're perfectly satisfied with living with a stupid answer of wave-particle duality. It doesn't make any sense. And they're not doing anything to find the truth.
Dramatic, the bend.
Again, we had the most perfect eclipse over the most advanced technical part of the world. 12 noon eclipse. I mean, straight, just as straight through the atmosphere as you could get. You could get the best photographs ever. I mean, Eddington's eclipse wasn't nearly as perfect. His was, out there on the horizon. It wasn't straight overhead. Middle of summer, straight overhead. Right? Most perfect eclipse you could get. And they didn't redo the experiment. Some amateur does it with a, doesn't even take photographs, the whole thing. I mean, slides, no high resolution telescope, no high resolution anything. Bullshit experiment. Nobody. With all of our advanced technology, nobody does the experiment. Clearly insane. 100th anniversary of Einstein's theory, and they still don't do the experiment. Does it make any sense? Doesn't make any sense at all.
When the light reaches the screen, it interferes with itself either constructively or destructively. We won't go into too much detail.
It sounded like I said destructively or destructively, But anyway, interferes with itself. It's just such bullshit. So again, more of this destructive and constructive. There's no way to understand that at all as constructive and destructive because it's multiple. In water waves, there's an actual doubling of the amplitude in one location and 0 at the other location. So we know the energy goes somewhere. It's moved from going in this place, it's moved to here. So nothing's destroyed. But in photons, you can't play that game. There's not, it's the truth, I would argue, that the photons clearly end up landing in one location and not landing in other locations. And clearly the photons are just like the waves. There's twice as much energy in one place as there would have been. So I'm just saying that they don't have a mechanism for how that happens. How do the photons move that energy? How do they constructively and destructively interfere? Because they don't cancel. Okay, a photon that was going here goes somewhere else. That's the fact. The energy does go somewhere else. So there is no destructive interference per se. There is this kind of interference that forces you to move the energy to a different location. But you don't destroy the energy.
Here, but constructive interference causes the wave amplitude to increase, giving rise to bright fringes, and destructive interference does quite the opposite, suppressing the wave amplitude and giving rise to dark fringes.
See, by their theory, they're almost saying that, okay, a single photon goes in, turns into two wave functions, and then somehow a double photon lands somewhere. That doesn't happen, okay? A double photon does not land somewhere. You can't make sense out of that. A single photon goes in, you can't make double photon or no photon. So I send a single photon in. It doesn't land on any, it doesn't destructively interfere and be destroyed. It actually lands somewhere. All right? So it just doesn't make any sense to say somehow it was destructively interfered, because clearly it landed somewhere, and it landed in one of the places where there's constructive interference. It didn't land in a place that was destructive. It landed in a place that was constructive. Okay, so it just doesn't make any sense on its face, because the only way they can use these terminology is the single photon goes in, splits in two, and doesn't land anywhere, because it can't land where it's supposed to, the dark place. It had to be destroyed. It wasn't destroyed. Every time the photon lands, it lands on a path of constructive interference. Every photon lands where there's constructive interference. No photon lands where there's destructive interference, or no photon is destroyed. So if no photon is destroyed, this doesn't make any sense. I mean, their analysis is just so trivial.
Light and dark fringes are regularly spaced in well-defined intervals. We call such a pattern
Well-defined intervals. They're just multiples of sine theta. That's all they are. The equation is n, which is the number 1, 2, 3, 4, 5, 6, 7 away from the center, times sine theta. It's clearly perfect multiples of exactly the same angle. They're perfect multiples.
interference pattern. The study of such things is unsurprisingly called interferometry. It's the exact effect that's behind the science of gravitational wave.
Right, and a pile of crap, right? Another big pile of unevidenced, unduplicated, anything untheoretically tested. We have no examples of this gravitational wave detector ever detecting anything called gravity anywhere on Earth. Anywhere in the solar system. It had detected no gravity anywhere. They showed us no test of a swinging ball over the mirror, and it detected the gravitational change. No evidence that it can detect gravity at all. None. Zero.
Detection, the discovery of the CMBR, and X-ray crystallography. Anyway, the point is that these interference patterns are the result of waves diffracting. But experiments can be done to show that electrons...
So again, it's rays diffracting, rays changing the angle at which they move, rays obeying Feynman's diagram, rays Compton scattering, however you want to say it. The same simple effect. The energy goes in, the electron moves a certain amount at a certain momentum. It can only change its position so much, and then it re-emits a photon at a new angle. That's all you need. You don't need any of this complex nonsense. All you have to understand is that surfaces are not simple. They're complex. A place full of one kind of atoms that are all attached to each other, and then a different material on the other side. Those places in the universe are not simple places. They're complex places. And when light has to travel through that place, it's not like there's surface. There's a big flat steel wall, and then there's where the photon's flying, and there's nothing in its way. Absolutely nothing. It doesn't hit anything. So there's not a choice between some wall and nothing. That's not what the photon is flying through. It's flying through a field of electrons that are on the outside of all the atoms, on both sides, on both materials, and those surfaces are charged in the sense that the electrons don't like electrons. So as you bring the surfaces closer together, the electrons are saying, I don't like looking at those other fucking electrons, I'm going that way. And one side has to go positive, and one side has to go negative. These are the rules, and they're just pretending none of those complex rules exist. We're just going to pretend that for a photon, it's a steel wall or nothing. And that's not the real world for an electron. That's not the real world for a photon.
do the exact same thing. We can do an experiment.
So electrons don't do the exact same thing. What they do is, where they don't even pay any attention, is they actually do create a pattern of on and off that goes slowly on, and slowly off, and slowly on, and slowly off. Very gradual. Where the photons create pretty much bars, duplicating the appearance of slits, in terms of surfaces. Very, very distinct on-off. Very little graduation between the on and the off, where the electrons have a lot of graduation. Now, the same math is being used, so how come the different results? Did they ever ask the question, well, why did the photons have a bias that doesn't show all that graduation? And why did the electrons show so much of it? They don't even ask the question, and the answer is kind of obvious and easy. The electrons have a force around them. They're reflecting something repulsive to each other, so they never really hit each other. They just deflect off of forces. Nobody jumps in a boat, kind of thing. Obviously, they do jump in the boat, but I just mean the only way they jump in the boat is because each electron has a bunch of swimmers swimming away from it as the other electron sees it. And so a bunch of swimmers, if I'm facing another electron, there's a bunch of swimmers jumping from his boat that are jumping in my boat. So I'm going to go away. That's all my only choice. And every swimmer I eject going that way ends up coming back at me again because it's going to jump into his boat and he's going to send another fucking swimmer back at me again. So no matter, every time I throw something at that other electron, he throws it right back at me. So I have to go that way. So electrons are different than photons. The patterns are different. They aren't identical. I mean, this is more of their trivial analysis. They just ignore the real effect and just pretend it's this simple thing they're going to describe when it's nothing simple at all. It's like saying a hammer is a squirrel. They're because they weigh the same. No, they're not the same. There's all kinds of nuance here that they just ignore. The fact that the double slit pattern doesn't just create one pattern. There's pattern superimposed on pattern. There's two patterns. The wave theory has no hope of explaining why there's two patterns. Wave interference won't explain the two patterns. And they just ignore its existence like it doesn't frickin' exist.
A bit like the photoelectric effect, where we have a cathode and an anode inside a vacuum chamber. If we apply a high enough voltage across the electrodes, electrons can be torn from the cathode and accelerated towards the anode. But if the anode is made out of a mesh rather than a solid sheet of material, most of the electrons will pass straight through, effectively creating an electron gun. This itself has a bunch of applications, but if
Yes, effectively. Yes, the point is because these electrons don't fly straight. So even though they're flying in a direction, they're being propelled because we're pushing them with more swimmers. We put a bunch of rowers or swimmers in the field from the dock, and the boat is sitting out there, and all of a sudden this wave of swimmers is going to hit that boat. They're going to jump in the boat, but the boat's still going to be doing all of this because it always has to move in the other dimensions. So it can't fly perfectly straight. It'll fly, basically in the direction, but it'll fly in the direction by snaking its way in that direction. So obviously, even though it's heading in a direction, it can't head for the exact low pressure because it's going to be ending up off course. So it'll end up missing the thing it was supposed to hit, and it'll go through the hole instead. But there is no pressure where the hole is saying go there. It's just can't turn fast enough to miss the hole.
If we fire the electrons at a thin sheet of metal with a photodetector on the other side, we actually observe circular diffraction patterns, as the electrons diffract through the metal in a wave-like nature. So electrons must...
So they draw conclusions. What obviously to an electron, every surface is going to that they can move through, that's thin enough for them to move through, is going to appear like a bunch of little slits. So obviously that's why it's going to create the pattern, is because it's basically going through another bunch of fields that are turning it and bending its path. There's a bunch of electrons you're pushing it next to, and they're going to be deflecting the electron as it travels. So if I put a field of electrons in front of an electron, it's obviously going to be moved in all kinds of more erratic directions because of all those fields created by all those electrons.
Also have some kind of wave-like nature as well. The wave-particle duality of matter is what led Louis de Broglie de Broglie to postulate the
De Broglie is okay with me, but whatever. So my particles have an associated wavelength. It's just made up. Volkswagens don't have wavelengths. Whatever. Corvettes, Mack trucks, me, I don't have a wavelength. If I run down the street, I don't have a wavelength. This is just nonsense. Electrons have momentum. They move. They don't have a wavelength. The truth is, though, that you give the electrons momentum with clumps, with rowers. Rowers apply the momentum. So the momentum comes in stages through the process of absorbing a rower and ejecting a rower. That's how electrons move. So they have to move in stages. Okay, but they don't have a wavelength. They have momentum.
The matter particles had some wavelength lambda inversely proportional to their momentum by Planck's constant h, or equivalently p equals h bar k. So with the wave-particle duality of all things firmly in place, physicists were able to answer a really important question. Why haven't all of the atoms exploded?
So he ends with some dopey trick question. Obviously they don't need to explode if you don't give all these bits momentum. So if all these electrons aren't spinning around here at 400,000 miles an hour, you don't really have that much of a problem in terms of a chaos problem. So if the electrons are just in positions, here, 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 here in space, and they're just wobbling in those positions in tension, then you can connect them easy. It makes sense to have a shared electron then, because the shared electron's in one position, both of them are sharing it, both of them are stuck to each other through that one connection, or two. And it makes sense. You don't need all this motion bullshit. Just have them magnetically. They're monopoles. They're magnetic monopoles. It's just so obvious, the proton and the electron. Model them as magnetic monopoles and you won't have any problem at all keeping them in their positions. The geometry will take care of itself. Alright. I mean, if you could go into space, you can do things with magnets if you can get out of gravity. You can do more things with magnets than you can do in gravity. Gravity screws everything up as it moves your magnets, and then it makes them move into new locations because it gives them too much momentum. But if you can keep things as still as possible, you can create all kinds of geometry with magnets. And if you could imagine having magnetic monopoles, you can create even more geometry where everything's stable. There's the equal amount of force pushing something away as there is attracting it in one direction. There's as much force pushing it one way as the other way, created by two different objects. The electron's pushing, the proton pulling, but not really pulling. And they're balanced. And it's theoretically solid. Alright, so enough. Hopefully I didn't go past my time again. That would be depressing. So, till the next time and such.